with module 11. Okay, so this module 11 here is about interrupt programming. So all of you can hear me, right? So in this interrupt programming, okay, you will learn about two types of interrupts. Okay, you will see what are the difference between interrupt and pollings, and then in the same time you will learn about two types of interrupt. We have two types of interrupt. One we call it as a internal interrupt, and the other one is timer interrupt. Okay, and then after that, okay, you will learn about the step to executing the interrupt. So what are the steps in order to write the interrupt programming, and how to enable and disable the interrupt by using certain codings. Okay, so this is the interrupt that I already told you. Okay, you have two types of interrupt. One is external hardware interrupt, and the other one is timer interrupt. And in the same time, you will learn about interrupt priority, interrupt inside interrupt. Is it possible to do interrupt while you doing the interrupt on that time? And the context savvy in the task switching. Okay, so without further ado, let's look at the introduction of interrupt. So a single micro P can serve several devices or tasks at the same time. Okay, means that you have one micro P. Okay, you can run one or two programs at the same time. Okay, there are two methods by which device receives service from the micro P. Okay, either you use it an interrupt, or the second one you use a polling. Okay, so what are the difference between interrupt and polling? Okay, so for the interrupt, okay, whenever any device need a micro P service, okay, the device notified by sending an interrupt signal. Okay, and then after that, what happens here is upon receiving an interrupt signal, your micro P or your CPU, okay, stop whatever it's doing and serve the device. Okay, so any program that associated with an interrupt called interrupt service routine, or we call it as a ISR, or sometimes we call it as a interrupt handler. So this is what happens when you are doing an interrupt. Means that, for example, okay, to simplify, for example, you have two programs. Okay, program A and program B. Okay, so currently, okay, you executing, okay, just you execute a program A. Okay, now you try to execute a program A. So this is your program M. You currently execute the program M. In the middle of the program A, what happened here is, okay, suddenly, okay, you give a, or you notify, or you give an interrupt signal to do the program B to your CPU. So what happened here is this program A will stop doing whatever it did, and then after that, what happened? Program B will start execute. Okay, so this is where you stop program A. Okay, so stop program A and then start with program B. Okay, and then after the program B finish, so what happened here is after that you continue back your program A until your program A is finished. So this is interrupt. Okay, while polling, okay, the micro P continuously monitor the status of a given device. When the status is met, it performs the service. After that, it moves on to monitor the device until each one is serviced. Okay, for example, you have two programs, program A and program B. Okay, so currently you do your program A, and in the middle here, okay, you try to, okay, now I'm going to do a program B. But due to this polling method, what happened here is the CPU will continue doing the program A until the program A is finished. And when the program is finished, then after that, the program B can start executes. Okay, so that is the difference between interrupts and polling. Okay, interrupt, once you notify or give an interrupt signal, what happens here is the program that you currently do, you need to stop and go to the program that you just you're going to interrupt. Okay, after that program or after that interrupt service routine is finished, then after that you continue back your program, your previous task or your previous program. Compared to polling, okay, even though you asking, okay, you currently doing a program A and in the middle of the program A, okay, you ask CPU, you're going to do a program B, but due to the polling method, the CPU will not give you chance to execute the program B. Okay, you need to wait until the program A is finished. Then after that, you execute program B. Okay, so this is the difference between interrupt and pollings. Okay, so what are the other differences between interrupt and polling? Okay, for the interrupt, efficient use of CPU, while polling not an efficient use of CPU. Why? Okay, because this one here, okay, for the polling, you need to wait until your program, okay, your current program is finished. Then after that, you can start with a new program, which is you wasting so much CPU there. Compared to interrupt, okay, if you have a higher priority program, that you can directly interrupt what you are the program that you're currently doing and do that higher priority task or program. Okay, so that is an efficient use of the CPU compared to poly. Okay, for the interrupt can serve many devices, which each device get attention of the CPU based on the priority assigned to it. Okay, so it depending on the priority of the devices or the priority of that interrupt. If that interrupt have a highest priority, that the CPU will entertain that that interrupt. After it's finished, then it go back doing what the previous task or program. Okay, so this one here cannot assign priority. So it checks all the device in a round robin fashion. So this one here, okay, it's something like, okay, you need to finish a certain program, then after that you can start with a new program. Okay, for the interrupt gate, okay, the CPU can ignore or mask a device request for service. Okay, so this one here depending on the interrupt priority. If that priority, the interrupt priority is lower than the program that you're currently doing, so the CPU will ignore that request. Okay, so for polling, you cannot ignore device request. Once the device request to do a program, then you need to do that program. You cannot ignore. And last but not least, avoid tying down the CPU. Thus, the waste time can be used to perform some useful tasks. Okay, so this is a by doing this, okay, you can get the efficient use of the CPU. Okay, for the poly waste much CPU time by poly device that do not need service. Okay, so not efficient use of the CPU. Okay, so let's look at the interrupt service routine. So for every interrupt, there must be interrupt service routine, your ISR. Okay, since when an interrupt is evoked or you're going to execute your interrupt or you trigger your interrupt, micro P runs the ISR. So every time the interrupt is evoked, every time you trigger your interrupt, the micropin must execute the ISR. Okay, generally for every ISR, there is a fixed location in a memory that hold the address of ISR. So this address of ISR will determine the priority of your interrupt service routine. Either is a higher priority or less priority. Okay, depending on the address. Okay, so this address here, okay, the group of a memory location set aside to hold this address of ISR called the interrupt vector table. So this is the interrupt vector table for ArcMega 32. Okay, you have a lot of interrupt handling here. Okay, from reset. Okay, and then this is the location inside of your program memory. Okay, this started is 0000. Okay, by looking at this one here, okay, the higher priorities is something like this. Okay, so this is the highest. So this is the lowest priority. Okay, so then you have an external interrupt request 0. So this is we call it as a INT0. External interrupt request 1. This is INT1. This is INT2. And then you have a timer counter compare mesh interrupt. Okay, so this is a timer interrupt. Okay, you have a several timer interrupt. Timer counter 2 overflow method. Timer counter 1 capture event. Timer counter 1 compare mesh if, etc. And then you have a SPI transfer complete, USAT, ADC conversion, EEPROM ready, analog comparator, store program memory and read. Okay, so the one that we're going to learn in this interrupt programming here is this one. Okay, external hardware interrupt, which is consists of three types: INT0, INT1, INT2. So this is an external hardware interrupt, and then timer interrupt. Okay, we will go more details on how to do this external hardware interrupt and timer interrupt. Okay, so let's recap, do some revision on the flash memory. Okay, we already learned about the program memory. Okay, so for ArcMega 32, we have three types of memories. One is a program memory, then we have a data memory and the EEPROM memory. Okay, for the program memory, or sometimes we call it as a flash memory, you can segregate into three bahagian, okay, three parts. Okay, the first one here, okay, started from 000 to 002A. Okay, so this is for the reset and interrupt vector section. So this is where you put, okay, where is my mouse? Okay, where this interrupt vector table location is. Okay, started from 000 until 00 to A. Okay, then we have an application flash section. This is where you put all the programming inside of this section here. And last but not least, you have a boot flash section. Okay, so this is your program memory. So let's look at the step in execute and interrupt. So how the interrupt will be executed. Okay, so this is the step that you're going to do in order to execute a certain interrupt. Okay, so upon activation of an interrupt, okay, so what happened here is the microP goes through the following step. Okay, first, it finished the instruction it's currently executing and save the address of the next instruction onto the stack. Okay, so what happened here is every time you request ISR or interrupt service routine, so the CPU will stop the program or the task that you currently doing. Okay, so upon the activation or upon the triggering of the interrupt, So what happened here? The program that you stop, okay, you currently executing, okay, will be stopped, and the CPU will take the address of the next instruction and put it to your stack. Okay, so this is where after the ISR is finished, then the CPU know that okay, next we need to continue from this address. Okay, we need to resume back to this address to continue your program you already stopped earlier. Okay, and then after that, after it save the address, okay, of the next instruction to the stack, so what happened here? It will jump to a fixed location in a memory called interrupt vector table. Okay, so it will go to your interrupt vector table and then see what are the ISR that currently triggered. Okay, either is a reset, external hardware interrupt, or timer interrupt, or etc. Okay, and then after that, the interrupt vector table direct the micro P to the address of the ISR. So what happened here is micro P will start execute the ISR until it reach the last instruction of the subroutine, which is RETI. So this is similar to what we learned in the subroutine process. Okay, every time you doing a call instruction, so what happened here? Okay, you need to save the next instruction to your stack, and after that you jump to the subroutine. So this is similar lah. Okay, and then after you finish your ISR, okay, every time you see the RETI, this is for the assembly language. Okay, so what happened here is upon executing this RETI, micro P return to the place where was interrupted and get the PC address from the stack. Okay, so every time the CPU execute the RETI, okay, which is written from interrupt service routine. So what happened here? The micro P will take back the address that they are already stored in the stack and put it to the program counter. So now the CPU know that, okay, now we need to resume to this location. Okay, so this is what happened every time the interrupt triggered. Okay, so let's look at this one here. So this is okay, I will show you the animation how the interrupt is done. Okay, so this is your program. Okay, so this program here is written in assembly language. Okay, basically we in this class here, okay, we use a C program in order to do the interrupt programming. Okay, so never mind, we just going to see what happened when the interrupt is triggered. Okay, so you initialize your okay, this part here, you initialize the stack pointer. Okay, and then this part here, you enable your interrupt, and this is where you initialize your input output parts. Okay, and then after that, okay, you do the main program here. Okay, so this is what happened here. You do the main program. Okay, you see here, this is your interrupt. Okay, you put a switch into your IN30, and what happened is when IN30 is pressed, okay, so means that you're going to do the interrupt 0. Okay, so this address here will be stored to your stack, and then the program counter know that you're going to do the INT0, and it will go to INT0 subroutine and do all the tasks inside of this interrupt service routine. And after that, okay, you're going to finish the ISR. Okay, upon executing the RETI, what happened here? Okay, sorry. Okay. Yeah. Okay, what happened here is, okay, the address that you store in the stack pointer will be loaded back to your program counter, and then after that you need to return to this address where you just trigger the interrupt. Okay, and then the CPU will resume this program. Okay, so this is what happened every time you execute the interrupt. Okay, so let's look at the interrupt unit in AVR. As I mentioned earlier, we have several interrupt based on the vector table. You have several interrupt starting with the reset, and then you have external hardware interrupt, timers, and others interrupts. Okay, so there are many sources of interrupt in the AVR, such as first is a timer interrupt. Okay, for the timer interrupt, you can divide it into two types. One by using the overflow interrupt, and the second one by using a compact mesh interrupt. Okay, so the overflow and compact mesh, okay, this thing here, you will learn more details on the timer programming. Okay, what is the overflow method? What is the compact mesh method? Okay, then we have the three interrupt of external hardware interrupt. Okay, which is we have a INT0, INT1, and INT2. Okay, since this is an external hardware interrupt, in order to trigger this interrupt, you need to put a switch. Okay, where you're going to put that switch, at what pins? Okay, so this is the pin that you need to put that switch. For INT0, you need to put it at port D pin number 2. Okay, for INT1, you need to put the switch at port D pin number 3, and for INT2, you need to put at port B pin number 2. Okay, so this location of the external hardware interrupt you need to memorize. Okay, then we have a serial communication USART has 3 input, and the SPI and the analog to digital converter. So we are going to focus on the timer and external hardware interrupts only. Okay, any question up until here? Ada soalan tak? Before we go more details on how to do the interrupt programming by using C language. Any question up until here? Okay, if no question, then we go to this part here. Okay, so this is the port D. Okay, a part beside you use the port D as an input port and output port, there are a special function that you can use for the port D. Okay, so this is the alternate function for the port Ds. Okay, so you see here, you can do the timer counter output, compare mesh output, OCP1, OC1A, OC1B. So now we are going to focus on this PD3 and PD2. Okay, so PD2 is for the external interrupt 0 input, while PD3 is external interrupt 1 input. So every time you're going to do the external hardware interrupt, okay, so you need to put a switch to this pin here. Okay, PD2, PD3. Okay, PD2 for the INT0, PD3 for INT1, while PB2 port B pin number 2 for INT2. Okay, so we recap. This is your Atmega 32. Okay, we have a total of 40 pin out. Okay, and then from these 32 pins, we can use it as an input-output port. A part of using it as an input-output port, it also have an alternate function. Okay, for example, for the port A, okay, this is your port A. The alternate function for the port A is you can use it as an analog to digital converter. Okay, instead of using it as an input-output, you also can use it as a analog to digital converter. And then, so this is another alternate function for port B. This is other alternate function for the port D, and this other alternate function for port C. Okay, so now we are going to focus on this port here, okay, because we are going to do the external hardware interrupt. Okay, we're going to see this port. Okay, so INT2 at port B pin number 2, and then you have a INT0 port D pin number 2 and INT1 port D pin number 3. So this is where you're going to put your switch in order to use the external hardware interrupts. So now we are going to write a program by using a C for the interrupt programming. Okay, so in C language, there is no instruction to manage the interrupt. Okay, so compared to what we call here assembly language, okay, so in order to write a interrupt programming, okay, you need to initialize the vector table. Okay, so this is a vector table. Okay, you have ORG0. So ORG0 means that this is for the reset, and then ORG0X02, this is for INT0. Why I'm telling you that OX02 for INT0? Because we're looking at this address here. Okay, by referring to this vector table, you see for the INT0, the addresses is 02. Okay, INT1, you need to declare, okay, initialize the vector table at 04, while INT2 at 06, and the rest will follow lah. Okay, so this is how you're going to initialize by using the assembly language. But for C programming, you no need to do that. Okay, so in the assembly, okay, here you see here you need to initialize the stack pointer as well. For the C programming, no need to initialize the stack pointer. Okay, so this is the things, okay, that you need to do in order to write the interrupt programming. Okay, step number 1. Okay, so just follow this step, then you can simply write the interrupt programming. Okay, step number 1, you need to include this file here. Okay, include avr/interrupt.h. Okay, so this is step number 1. Okay, so memorize this step. Step number 1, include, okay, hashtag include avr/interrupt.h. Okay, is previously you already hashtag include avr/io.h, correct? Now you need to include another header or another library, which is we call it as a interrupt file. Yeah. Okay, then after you include this file, then step number 2, okay, you need to enable the interrupt. Okay, there are 2 locations that you're going to enable the interrupt. Okay, one is at GICR. Okay, if you're using a external timer interrupt, then you need to enable at GICR. If you're using a timer interrupt, then you need to enable at TIMSK. Okay, this is register that you need to enable. Okay, whenever you use the external timer interrupt, and this is if you're using the, oh sorry, this is for the external hardware interrupt, and this is for the timer interrupt. And the second location you need to enable your interrupt is at your status register. Okay, so recall that inside of your status register there is a flag called I. Okay, so you need to enable your interrupt at this status register at a flag I. Okay, How to enable the I in the status register? Okay, you can simply write the SEI to enable. Okay, so SEI to enable or CLI to disable the interrupt globally. Okay, and step number 3, what are you going to do? Okay, you need to do the ISR. Okay, your interrupt service routine. Whatever task that you're going to do, every time you trigger the interrupt, then you put it inside of your interrupt service routine. Okay, so in order to uh, write the ISR, okay, you need to write in the following structure. So ISR and then followed by the interrupt vector table name. Okay, make sure that the name must follow the interrupt vector name. Okay, and then open curly bracket, close curly bracket, and inside here is your program. Okay, so for the interrupt vector name, okay, must use the ISR name in table here. Okay, so make sure that the name is correct according to this table. Okay, if you're going to use the INT0, okay, so so your ISR should be ISR INT0 underscore vet and then open curly bracket and close curly bracket. Okay, make sure that you write exactly same with this table here. Okay, if not, then your interrupt will never happen. Okay, so this is the step. Okay, you have 3 steps here. Okay, include this file avr/interrupt.h. Okay, and then enable your interrupt. Okay, one at the GICR if you use the external hardware interrupt, or TIMSK if you use the timer interrupt. And the second location you need to enable here is at the I flag inside of your status register. And after that, after you enable all the interrupts here, then you will start with your interrupt service routine. Okay. So now, okay, we're going to see how to enable and disable an interrupt. Okay. So upon reset, okay, every time you switch off or you turn off your micro P, you reset your micro P, all interrupt are disabled. Okay, so none will be responded to by micro P if they are activated. Okay, so that's why we need to enable them first in order to use the interrupt. Okay, because why? Because every time you switch on your micro P or you switch on your CPU, all the interrupt are disabled. Okay, so the interrupt must be enabled or unmasked from micro P to respond to them. Yes, so how? Okay, there are 2 locations that we need to enable. One inside of the status register, the other one inside of the interrupt register. Okay, either GICR or TIMSK. Okay, now we're going to see how to enable the interrupt for the status register. Okay, so the bit 7 in the status register responsible to enable and disable the interrupt globally. Okay, you see here, this bit 7 is used for enable and disable the interrupt globally. Okay, so the bit 7 or the I flag must be set high to allow interrupt to happen. Okay, how to enable the I flag? Okay, you can enable it by use this instruction. Okay, by use this coding SEI open bracket close bracket. Okay, and then followed by semicolon. Okay, to disable, okay, just write CLI and then followed by brackets. Okay, so this is for the status register. To enable interrupt, you have two places to enable that. Okay, one at the status register, and the second one dekat your interrupt register. Okay, so interrupt register, there are two interrupt register. One, we call it as a GICR, and the second one is a TIMSK. Okay, TIMSK for the timer interrupt, while GICR for external hardware interrupt. Okay, so there are some IO register holding the interrupt enable bit, even though you already set with one. Okay, even though you enable here, you disable here, you cannot do the interrupt. You cannot trigger the interrupt. Okay, if you enable the interrupt at your interrupt register, but you forgot to enable your interrupt at I flag, so again, you cannot activate the interrupt. Okay, you need to enable both status register and interrupt register to trigger an interrupt. Okay, so let's look at the okay, first is TIMSK. So this is your TIMSK. TIMSK stands for timer interrupt mask register. Okay, so you have 8 bits. Okay, so this TIMSK is actually inside of your IO registers. Okay, so here, okay, if you see here, okay, the one that you need to know here is this one. I think, sekejap I think all of them you need to timer 0 compare mesh, timer 1 capture interrupt. Okay, so all the bit you need to know except this bit here. Okay, so bit 0 and bit 1, this is for timer 0. Okay, and then this bit to this bit, this is for timer 1, and this one here, this is for timer 2. Okay, as I mentioned earlier, okay, each of this timer, there are two methods. One, overflow method, and the other one is compare mesh method. Okay, for example, okay, if you're going to use the timer 0 overflow method, so you need to enable at this location. T0IE0 stand for timer 0 overflow interrupt enable. If you put 0, you disable the timer 0 overflow interrupt. If you put 1, you enable the timer 0 overflow interrupt. Okay, so OC, this is for the compare mesh. Okay, so how you, okay, and OCIE0, this is a compare mesh for timer 0. Okay, you see this 0 here, this is belong to timer 0. Okay, if it started with T, so you know that this is using the overflow. If it started with OC, then this is using the compare mesh. Okay, and this one here you see 1, 1, and 1. Okay, so this is for the timer 1, and 2 and 2 here, this is for timer 2, and the rest is similar lah. This is OC for compare mesh. T0, this is for overflow method. OC is for a compare mesh. T0 for overflow method. Okay, so this is where you're going to enable if you're using the timer interrupt, okay, which is inside of your TIMSK register. Okay, yeah.
What's the use of the bit between timer 1 and timer 2?
Which one? This one, yeah? Is it
TICIE1.
Okay, this one here is a timer 1 interrupt capture interrupt enable. Okay, so this one we will not cover on this part here. Okay, we only cover on this either overflow method or compare match.
Okay.
Okay. Okay, so this is for the TIMSK, and then you have another interrupt register called GICR. Okay, so GICR stands for General Interrupt Control Register. Okay, so for the GICR, okay, so this one is if you're going to use the external hardware interrupt. Okay, every time you use the external hardware interrupt, then you need to enable inside of your GICR. Okay, again, your GICR has 8 bit. Okay, ada 8 bit. Okay, so where is the bit that you need to focus? Okay, to emphasize. Okay, so only 3 bit that you need to enable. Okay, either bit 7, 6, or bit 5. Okay, for bit 7, this is for INT1. Okay, this is for external interrupt request 1 enable. Okay, if you put 0 here, you disable. If you put 1, now you enable your INT 1. Okay, then followed by INT 0. So this is for the external interrupt request 0. And this one here is INT 2. Okay, what about the rest of the bit? The rest of the bit you just ignore, or you can simply put 0, 0, 0, 0, 0 here. Okay, we only emphasize or focus on this 3 bit for the GICR. Okay, so now let's look at the external interrupt programming. Okay, how to write the external interrupt programming. Okay, so again, okay, so this is just for the recap. There are 3 external hardware interrupt, which is INT0, INT1, and INT2. Okay, and you need to remember that INT0 located at the PD2, INT1 at PD3, and INT2 at port B pin number 2. Okay, for the C programming, okay, no need to remember the vector table location. But if you use the assembly language, then you need to remember this part, this vector table location. Okay, so the hardware interrupt must be enabled before they can take effect. Okay, where you're going to enable the hardware interrupt? Okay, by enable at GICR register. Okay, which is your general interrupt control register. Okay, so there is 3 locations that you need to enable, which is at bit 7, 6, or bit 5. Okay, so let's look how to enable INT0. Okay, you're going to use an INT0. Okay, so how to enable your INT0? Okay, to enable the INT0, you can simply write GICR equal to, okay, where is your INT0? So this is your INT0. Okay, to enable your INT0, you need to put 1 to this bit. Okay, what about the rest of the bit? Okay, the rest of the bit, you just simply put 0. Okay, so 0, 1, 0, 0, 0, 0, 0, 0. So now what happened here? Okay, since this one here, you put 1. So now you enable INT 0. Okay, what about if you're going to use 2 interrupt? For example, INT0 and INT2. So how to do that? How to enable INT0 and INT2? Okay, you can simply write GICR equal to 0B 0 1 1 0 0 0 0 0. So this is INT0 and this is INT2. What about if you're going to what we call here, enable all the external hardware interrupt? Okay, you're going to use the INT0, INT1, and INT2 in your program. Okay, so just simply write GICR equal to 0B111 0 0 0 0 0. So now you are using INT1, INT2, and INT0. 0 in your program. You already enable all the external hardware interrupt. So this is how you're going to enable the interrupt, the external hardware interrupt in the GICR. Any question?
No, Doctor.
Okay, so let's look at this statement here. The INT0 is a low-level trigger interrupt by default. Okay, so when a low signal is applied to PD2, the controller will be interrupted and jump to INT2 vector in the vector table to service ISR. Okay, means that, okay, so you have a PD2. Okay, so you connected to your switch. Okay, since the interrupt is a low level trigger, okay, all the external hardware interrupt is a low level trigger. Okay, for the low level trigger, you need to use the active low switches. Okay, so this is your switch. Okay, I just simply this quite similar. Okay, so this is your PD2, and then okay, so this is an active low switch. Okay, so you need to remember how the circuit of active low switches and active high switch. Okay, so this is active low. Okay, sometimes we can put the resistor here. Okay. Okay, so this one no need to put resistor also. Okay. Okay, as long as you put a resistor here. And then for the active high, okay, so the switch that you need to connect it here something like this. Okay, so this is your micro MCU, your micro P. And then this go to ground. This is your switch. And this is your VCC. Okay, and then you could put, okay, here also can. Okay, so this is active high and active low. Okay, so make sure that the switch connection is correct lah. Okay, for the active low switch and active high switch. For interrupt, we need to use the active low switches. Okay, why? Because the interrupt is a low level trigger. Okay, every time you press the switch and it will give input 0, then the interrupt will be triggered. Okay, if not, then the CPU know that, okay, you not triggered any interrupt. Okay, so let's look at this one here. Okay, let's look at this example. Okay, assume that the INT0 pin is connected to a switch that is a normally high. Okay, normally high. What is normally high? Okay, means that if you not press the switch, it will give you output 1. If you press the switch, it will give you output 0. Means that it is using an active low switch. Okay, write a program that toggle port C pin number 3 whenever the INT0 pin goes low. Okay, so now first thing first, what you're going to do? Okay, we'll draw our Atmega 32 circuits. Okay, since this is INT0, so INT0, you need to put your active low switch at what pin? At PD2. Okay, so since you're using the INT0, so make sure that your switch is connected at your PD2. So this is your PD2, port D pin number 2. You connect to your active low switches. Okay, so actually you need to have the VCC here and then a resistor. Okay, so this is your active low switch. Connect to PD2. And then you have a port C3. Okay, so port C3 here become your output port. Why output port? Because you're going to toggles. Okay, every time the switch, okay, every time you trigger the INT0. So every time you trigger the INT0, the value of your port C will be toggled. Okay, if it is started with a 0 and then it will toggle to 1, and then if it is you press again your INT0, okay, you trigger your interrupt and then it will go back to 0. Okay, so this is the circuit. Okay, so now you're going to write the program. Okay, so the first step, what is the first step to write the interrupt program? Okay, first step, okay, you need to include this file. Okay, include avr/interrupt.h. Okay, so this is the step that you need to do. Okay, include this file. Okay, so you started with your program. Okay, first hashtag include. Okay, so this is the must lah. avr/io.h, and then the second one here file that you need to include is include avr/interrupt.h. Okay, so this is the first step. Okay, and then you start with your main program, int main void. Okay, open curly bracket and close curly bracket down there. Okay, next, what are you going to do? Okay, after you include the avr/interrupt.h, okay, second, you need to enable interrupt. Okay, there is two locations to enable interrupt. Okay, one at GICR. Why GICR? Because you're using the INT0. Okay, external hardware interrupt. So you need to enable at GICR. The second one at status register. Okay, before we enable the interrupt, okay, we need to initialize our input-output port. Okay, our input-output port. Okay, so in this case here, okay, port C pin number 3, okay, is your output. So you need to make it as a output port. So DDRC sama dengan OXFF. Or you can simply DDRC equal to, because this is only port C pin number 3. Okay, so you can simply write something like this. Okay, shift 1 to the shift 1 3 times to the left. Okay, which is you're going to put 1 to your PD3. Okay, either you make it all the port C as an output port, or you can simply only one PD3 is initialized as a output port. Okay, then after that, here, okay, PD2. Okay, so for the PD2, okay, you see here, this PD2 is connected to the switches. Okay, so DDRD. Okay, so make sure that 0B, okay, you can simply 1111 1011. Okay, put 0 at PD2. Okay, so now what happened here is, okay, only PD2 become input port. Okay, the rest is output. Okay, since this one is connected to the switch, next what you're going to do? Okay, you need to do what? Enable the pull up resistor. Okay, every time you connected to the switch, okay, enable the pull up resistor. Okay, so port D equal to 0B0000010. And then after that, we can enable the interrupt. Okay, so first we enable a GICR. So GICR. So what value that you need to put to your GICR? Okay, recall back, this is your GICR. Okay, there is 3 location that you need to enable. Okay, so this is belong to INT1, this is INT0, and this is INT2. Okay, since you're using the INT0, so this is where you need to enable. What about the rest? Okay, the rest you just disable lah. So 0, 1, 0, 0, 0, 0, 0, 0. So enable INT1. Okay, then after that, enable your status register. Okay, so I just simply SEI bracket and semicolon and use a while one. Why you need to use a while one? Because you need to monitor this interrupt continuously. Okay, while one. Okay, so this is your main program. Okay, so this is your main program. Okay, after you finish your main program, then after that, okay, we're going to do the interrupt service routine. Okay, so what is your interrupt service routine? Okay, this is your program that you need to write lah. Every time you do the interrupt service routine, which is your port C pin number 3 will toggle every time you trigger the interrupt. Okay, so I just put here. So this one. Okay, so how to write the ISR? Okay, so you need to create your ISR subroutine. Okay, so ISR and then the interrupt name. Okay, so this name here must follow this table. Okay, okay, the table I give you earlier. Okay, this table. Okay, since this one here you're going to use the INT0. Okay, so you need to use this name here, INT0 underscore vet. Okay, so make sure that you need to follow this table. Okay, it is a case sensitive. Okay, if this is using a capital letter, then you need to use a capital letter. If you use a small letter, okay, then you need to use the lowercase. Okay, so INT. Okay, since we're using the INT0, so INT0 underscore vet. Make sure that the name is correct. Then you open clear bracket and close clear bracket. So this is the program that you need to write inside of your interrupt service routine. So in this case here, okay, you're going to toggle your port C pin number 3. Okay, how to toggle port C pin number 3? Okay, you can simply use the port C equal to port C, and then what symbol is this? Okay, can you tell me what symbol is this? What operation?
XOR.
Okay, you're doing the XOR. Okay, so XOR is used. Okay, you use the exclusive OR to do the toggling process. Okay, so actually this one here, okay, this line is actually similar to this one. Okay, port C equal to port C. Okay, whatever the value of port C, and then you do the exclusive OR 0B0000. Okay, and 1000. Okay, so this is shift 1 to the left 3 times is actually this number. okay, you will get this number. Okay, this is the shorthand to write this number here. Okay, then so this is your interrupt service routine, and then you close your service your subroutine lah. Okay, your interrupt service routine by closing the curly bracket. So actually, this curly bracket is your RETI. Okay, you're going to return from your interrupt service routine. Okay, so this is how you're going to write down the interrupt programming by using the external hardware interrupt. Okay, now let's look at this the red sentence here. So what happened by the time microfi finish ISR exit and INT0 still low? Okay, means that, okay, okay, we just I just use a simple situation here. Okay, you have two programs. Okay, program A and this is a program B. Okay, program A, you're going to count from 1 to 10. And program B, you're going to count from 20 to 30. Okay, so program A is your main program. And program B is your ISR. Okay, so now you start with your main program. Okay, you're counting 1, 2, 3, 4. Okay, suddenly, okay, you press this switch here. Okay, so this is your program A, PA, and this is PB. Okay, so you currently do this program here, and then now you trigger your interrupt. Okay, by pressing this switch. So what happened here? So now the CPU will stop counting and start with count 20, 21 until 30. Okay, when it finished count 30, what happened here is, by right, it's supposed to continue with 5, 6, 7, okay, counting back your program A. But by the time it has finished the count 30, you still press your switch, okay, this is your switch. Okay, your switch still give logic 0. Okay, means that, okay, so as I mentioned earlier, okay, the interrupt is a low level trigger. Every time the CPU sends the logic 0 on your interrupt switches, it will what we call here, it will trigger the interrupt. Okay, so what happened here? Okay, since after you finish count 30, which is you finish your ISR, but you still press the switch. The switch still give logic 0. So what happened? Okay, you cannot continue with 5, 6, 7. Okay, you need to go back to your interrupt service routine, which is you started again 20 until 30 until, okay, the CPU sends logic 1 here. Then after that, it will started with 5, 6, 7 until 10. Okay, so this is what happened. Okay, by the time microfi finish your ISR, but your INT still give you logic 0. So the question is how to overcome, okay, this kind of situation. Okay, means that it only trigger the ISR one time every time you press your switch. Okay, you get what I mean? Okay, means that even though, okay, even though by this, okay, so this is the, okay, so this is a switch, okay, so you still give us logic 0, okay, this is okay, now you start from 1, 2, 3, 4, and then suddenly you press your interrupt, okay, so you're going to do a counting from 20 to 30, and the CPU will jump to your program B, count 20, this sequence here, 20, 21 until 30, and then, but in this time here, okay, the logic still 0, but now what happened here is, okay, the CPU stop your interrupt service routine and continue with your program A, which is start resume 5, 6, 7 until 10. How to do that? Okay, the first case here, okay, this one, it will trigger the interrupt again, but now, even though the switch still pressed, okay, but it will finish the interrupt service routine and resume back the program A. So how to do that? Okay, to do that, we can use the edge trigger. Okay, so this is the edge trigger. Okay, there is another what we call here, another setting that you can do, okay, in order to combat this situation here where you only want to what we call here, you only want to trigger the interrupt one time, even though you still not release the switch. Okay, so by using that, okay, you can do that by using the edge or level trigger. So there are two types of activation for the external hardware interrupt. First, by using the level trigger. So the earlier we using a level trigger, and the second one by using the edge trigger. Okay, the level trigger is available in INT0 and INT1, while edge trigger is available in INT0, INT1, and INT2. Okay, so this is where you're going to overcome the previous situation or the previous problem. Okay, so there are two registers that you need to know. Okay, one is a MCU CSR. Okay, so this is for the INT2 only, while for INT1 and INT0 you need to do a setting at MCU CR. Okay, so let's look at the MCU CSR first. Okay, so this is your MCU CSR. So this stands for MCU Control and Status Register. Okay, so it is 8 bits. Okay, so you need to focus on this bit only, bit 6 inside of your MCU CSR. Okay, so when you put 0 at this bit, okay, so this one here, this is a falling edge trigger. So every time, okay, so every time the CPU sense the falling edge, then the interrupt will be triggered. Okay, if you're going to use the rising edge, okay, then you need to put 1 at this bit here. If you put 1, so every time the switch sense the rising edge, which is you release your switch, then the interrupt will be triggered. Okay, previously, okay, we the interrupt trigger whenever it sense logic 0. Okay, now we're going to use the level trigger in use the edge trigger in order to overcome, okay, this situation here. Okay, So this is for the INT2. Okay, so INT2, we need to do a setting MCU CSR. Okay, for INT2, there is no level triggered, only edge triggered, either 0 or 1. 0 is a falling edge, or 1 is the rising edge. Okay, where you going to put here? At bit 6 inside of your MCU CSR. Okay, but for this one here, okay, for INT2 and INT1, INT0 and INT1, you can set it in the MCU-CR register. Okay, MCU-CR is MCU control register. Okay, so where is the bit that you need to focus? So this bit here, this 4 bit. Okay, bit 0 until bit 3. Okay, so this one, this is for INT0, and this 2 bit for INT1. Okay, so this is the setting that you can do. If you put 0, 0, then what happen here is, okay, the low level of INT0 will generate an interrupt request. If you put 0, 1, okay, any logical change from 0 to, okay, 1 to 0 or 0 to 1 will generate an interrupt request. If you put 1, 0, so this is a falling edge triggered. 1, 1, this is a rising edge triggered. Okay, similar to INT0, if you put 0, 0, low level triggered, 0, 1, any logical change, either from high to low or low to high. 1, 0, only falling edge. 1, 1 is rising edge. So in this case here, okay, you can put another code here in between here, which is you can put MCU CR equal to 0B 0 0 0 0 0 0 1 1. Okay, for the rising edge trigger. Okay, to overcome, okay, or to avoid this thing happen. Okay, which is the interrupt only will trigger one time every time you press the switch. Okay, so this is only the interrupt only triggered if you use the what you call rising edge. Okay, the interrupt only trigger whenever you release the switch. If you use the falling edge, the interrupt only trigger when you press the switch. Okay, so this is when you release. Okay, when you release, the interrupt will trigger, and if you use a falling edge, when you press the switch, the interrupt will trigger. Okay, so how to program the level trigger? Okay, so this is an example how to program the level trigger. Okay, show the instruction A, make INT0 falling edge triggered. B, make INT1 triggered on any change. And C, make INT2 rising edge triggered. Okay, so this one here, for the INT and INT0, so you need to know that this is the bit that you need to look at. Okay, so this is for INT0. This is for INT1. Okay, so this is for your MCU-CR. Okay, for INT2, okay, you need to use the MCU-CR register. Okay, so where is the location? This is the location, bit 6. Okay, so here, A, make INT0 falling edge triggered. Okay, so how to make a falling edge triggered? Okay, so this one here, actually, if you put 0, 0, it is a level triggered. 0, 1 is, sorry, any change. 1, 0, falling edge. 1, 1, rising edge. Okay, you need to remember this thing lah. Okay, this setting here. Okay, 1 0 falling edge, 1 1 is rising edge. Okay, so now A make int 0 falling edge trigger. So you can simply write MCUCR equal to 0B0000 00. Why 00? Because I don't want to make any changes on the int1. Okay, I only focus on the int0. So falling edge, what is a falling edge? 1 0. Okay, if you change in hexadecimal, then it's equal to OX02. Okay. B, make int1 trigger on any changes. Okay, which is any changes we need to put a 0 1 lah. Okay, so you can simply write MCUCR equal to 0B0000, and this is where you need to set. Okay, any change is 0 1, so 0 1 0 0. Okay, or you can simply put something like this lah. Okay, MCUCR put 1 to ISC10. Where is ISC10? So this is the location of ISC10. Okay, so it is actually equivalent to this one lah. Okay, and then after that, make INT2 rising edge triggered. So how to make INT2 rising edge? Okay, so this one here you need to put it at MCUCSR. So MCUCSR 0B0, and this is bit where you need to put the settings. Okay, in this case here, rising edge. If falling edge is 0, and then if rising edge is 1, so you need to put 1 lah kat sini. Okay, so the value here is MCUCSR equal to 0B01000000. Any question up until here? Ada soalan tak? Okay, so again, so this is the previous examples. Okay, rewrite previous switch examples so that whenever INT0 goes low, it toggle port C, okay, pin number 3 only once. Okay, so you can use either you're going to use a falling edge trigger or rising edge trigger. So the setting here you need to put here lah, MCUCR. Okay, you can put a 0B00000010, okay, for the falling edge, or you can simply put the MCUCR 0B00000011 for the rising edge. Okay, as long as the interrupt triggers 1, okay, every time you press the switch, then you can use either falling edge or rising edge. Any question? This is for the external hardware interrupt. Okay, if no question, then we go to timer interrupt programming. Okay, I think we stop here. Okay, this one we continue next week. Okay, tak? Is it okay with you?
Yeah, right there.
Okay, we stop here and then we continue.